The silent architecture of energy, where fields vanish in focus. This exploration bridges the gap between abstract physics and digital visualization, revealing how static electric and magnetic fields inhabit the space around us. At its heart is a vanishing act, a mathematical proof showing that when these fields are contained within specific boundaries, their total combined energy effectively cancels out, simplifying complex calculations into a clean, logical zero. The tale of two distributions. The sheet centers on a fundamental contrast between the two pillars of electromagnetism. The focus flare of electricity. Imagine a single-point charge. Its energy is a burst of intensity, packed tightly around its source. As you move away, this energy doesn't just fade, it collapses with extreme speed. By the time you reach the distant edges of the system, the energy has essentially evaporated, proving that for localized charges, the action is almost entirely at the heart. The disciplined glow of magnetism. In contrast, consider an ideal solenoid, a coiled wire. Here, the energy refuses to dissipate into the void. Instead, it is perfectly disciplined, held in a uniform and constant state strictly within the interior of the coil. It is a masterclass in containment, showing how magnetic energy can be trapped and put to work within a well-defined volume. Bridging the invisible with the visual. To make these invisible forces tangible, the study utilizes a visual and orchestra framework. Rather than relying on static equations, the journey is told through dynamic blueprints, sequence and state diagrams that map the evolution of understanding, guiding a learner from the basic building blocks of vector math to the mastery of complex field theories. The expanding boundary. Python-based animations that simulate a Gaussian surface growing toward infinity. These visuals prove a critical point. As the boundary expands, the leaking energy becomes so thin that it eventually disappears, justifying why we can ignore distant boundaries in real-world physics. Computational art. The transition from paper derivations to digital simulations, where the steep decay of a point charge is contrasted against the steady, rectangular profile of a solenoid's internal field. The final synthesis. Ultimately, this is a story of independence and geometry. It proves that in static systems, electric and magnetic energy densities can exist together without interfering in a way that disrupts the total balance of the system. By mastering the geometry of these fields, scientists and engineers can better predict how energy is stored, shielded, and utilized in everything from simple electronics to advanced plasma physics.